think some people asked about the slides and the presentation. If there is a place where we can put them, as I understand that they are already in the video, but if there is a need to upload them to some kind of like server, just let me know and we can just upload them. So this is definitely no problem. I will go a little bit back just to make sure that we have a continuation of where we stopped last lecture. We stop a little bit after this one, but let us go back to projective transformation because this will be the focus of this lecture. And I think understanding the projective transformation and the hierarchy of transformation kind of simplify the understanding of the perspective and the projective mapping in general. So in the last lecture, we say that projectivity is a transformation which is like linear transformation. We have very similar requirement of this transformation. It's only we require that it preserve linearity, and it's also which is mean collinear lines, which are points which is along the same line remain along the same line after this projection. And it's pretty much, or in general, we can actually perceive it as a mapping or linear transformation, which could be represented as a 3x3 matrix. And this is practically define the projective transformation space. The only thing that this is what we will have, it will be map like points from the projective. Just kind of bear in mind that we are talking about the projective 2D space. All this, like this part will be more into the 2D space. So we are talking about projective mapping of points in plane to another points in another plane. This is the idea of projective. So if a point will be in any point will be mapped, its image will be just by multiplication the transformation matrix H by X. And this since the transformation is 3x3, it's 8 degrees of freedom because we can always determine like one point and compute the other, or practically it's a ratio. This is all about is the projection transformation, the only property which is preserved from the source and the destination, which is mean before the mapping and after the mapping, is what we call the cross ratio, which is I will define it later. Now, this is practically how we will perceive the projective transformation. It's map points from this plane into this plane. So if we have the plane pi, which is with coordinate system xy, would be mapped to different plane, which is coordinate system x prime, y prime. And this is the point. This is what we call the mapping. So if we have x1, x2, x3, the point will be mapped by the transformation into another point. Now, let us look at something which is kind of like example, which will make things easy to understand. This image was taken, and now we see there is a perspective distortion. Why we see there is a perspective distortion? These are supposed to be rectangular window, but they are not. This is the perspective distortion. And if we see these like lines, which is they are in reality they are in reality they are parallel, but if we continue these lines, they intersect somewhere in the infinity. This is what we call the point in the infinity, or we often refer to this as the vanishing point. Now, what we would like to correct the perspective distortion, which is we often refer to this as like rectification, but it's not really exactly. Later we'll see what we mean by rectify. But here, this is what we will do. We'll try to remove all the perspective distortion and create an image which is the same image but without the perspective distortion, as if we actually take this image using orthogonal or parallel projection camera or orthogonal camera. That means there is no perspective distortion. So now how we are going to computing the mapping of every point here to the new point will be done through projective transformation, which is mean this is the first image will be this plane, the second image will be this plane. What we are interested to find this mapping. You see, this is what we have. We have here one plane, which is this image, and we want to move it to transfer it to this plane. Bear in mind, we assuming this is a projective transformation, which is because this is perspective, it's definitely projective. Now, what we want to do, if someone give us these 4 points in the source image and tell us these 4 points will be mapped to these 4 points. Now, let us take very simple example. If we take this point x prime, any point, let us call this x, y, this point. This will be the image of this point, x prime, y prime. Now, if we take, let us assume our transformation is h, exactly what the one we just have seen here. So if I take now x, replace this by x prime, y prime, what this will be? Because we are in the 2D, this will be, because this is homogeneous coordinates. So this will be definitely not like a 0 in this case. And what we will do, we will multiply this to get x prime, y prime in this. And now what we want to find all this h11, h12 to h33 values. That's simple. We compute 2 equations, x prime equal h11x plus h12y plus h13, because we take 1 as the homogeneous coordinate value. And then we take h, this will be divided by h3 1x, h3 1, 2, and so on. So we get 2 equations. If we can simplify, this will be x prime will be equal this one, and y prime will be that one. This is from 1 point, give us 2 equations. If we have 4 points with their corresponding points, that means we know correspondence between these 2 points. How many equations we will get? 1 point, like a pair of points, give us, or like 1 point and its image give us 2 equations. 4 of points and their images will give us 8 equations. That's enough to resolve an 8 degree of freedom. Yes, because we have 8 equations, and this is how we will resolve this. This will give us the solution for the transformation. This will enable us to determine all the h11, h12 in this transformation h. Now we take every point after we compute the transformation. We take every point here and see where it will be mapped here. Or it's the opposite. We take a point here and take the inverse and to say where it came from. And this is how we will do the projective mapping. We will do this also correction with vanishing point later, like in this course, maybe next lecture we'll talk about using the vanishing point in order to do the perspective correction. Now it's just like to remind me of the vanishing point, that if there is a lines in the original image and we continue these lines, this line will intersect to some point, which could be in the infinity or like far away out of the image, but this will be the vanishing point for us. This is clear? Is that clear how we solve? And now it's also clear why we have 8 degrees of freedom. Now, it's not always, for example, one thing which is, we could make this, normalize this matrix by dividing by the entire matrix by h33, yes? In general, this would be correct, unless h330, yes? And in this, it could be 0. And in this case, it's not always possible to get H331. Because if it's 0, we cannot kind of normalize according to H33. So this is, but it's still, this is 8 degree of freedom. Now let us look at some examples of a projective transformation. What we will have, the first on the on your left side, we have two images, and they are projective transformation between two images induced by a world plane. What we have, this is the plane surface, which is, we get two images of this plane, and now we have points in this. Now we can actually compute the transformation from image 1 to image 2. And this will be projective transformation, which is exactly the same example that if I have an object here, I take one photo of this object, of this plane, and then I take another photo of this plane. I can compute the transformation from this image to this image using the projective transformation. Actually, the mapping from this image to this image is a projective transformation. Another example, which is if we have a camera, which is the camera now is not like this. I took one photo from here and took one photo from here. I take the same like camera. You take a photo from here, then you rotate your camera, take another photo, and then you can compute between them a projective transformation. Actually, the transformation between the points, which is within the two images, are projective transformation. Points which are not shared are not there, because we cannot map point to point which doesn't exist unless we assume our image is infinite, so it's all the points, the visible points are there. It's also if we take the projective transformation also is a mapping of an image of an object. For example, this is the part of the house and its shadow. And we could also do this mapping as projective transformation. In this case, note that we don't assume that the rays coming from the sun are parallel. So they are we assume they are a point, which is not always the case. Okay, now let us look into a little bit mathematics. You need to to bear with me the first part of the course. We are going over some mathematics, which is refreshing your memory. So if you have something which is not clear, just raise your hand and ask about this. Later we'll look into more algorithmic, but based on this mathematics. In general, this is not complicated mathematics. It's just it looks as it's complicated, but practically what we are talking about, matrices, which is either 3 by 3 or 4 by 4, or vectors, which is in the two domain, which will be either non-homogeneous xy or homogeneous, which is xy and z, or xy and w. Now, if we have if we think about the distortion, what we will have under the projective transformation, we know that if we have projective transformation H, every point xi will be mapped to point xi prime. This is how. Now, how lines will be mapped? Points will be mapped to a point, as we saw earlier. How lines will be mapped? Lines is we could take 2 points and map them to a new points. 2 points is not really will give us let us take 3 points and map them using projection transformation to map them to another 3 points. It will be mapped to a line, we know that. The line will be mapped because projective transformation preserve collinearity. Now, how this line as a whole will be mapped to the new line? It's what we know, that the points in this line, now we know because projective transformation guarantee collinearity. So if we have any point in this line, and map it to a new line, which is, we will call it L prime. So if we have L prime transpose, as we say, like in the previous lecture, like, or the one before, like this matrix multiplied by, or it will be a vector in this case, multiplied by the point xi, will give us 0 because this point xi lies on a line. So let us just kind of like to clarify this. I have this line L, and it will be mapped to a new line L prime. So what I know that a point which is x, any point xi, will be mapped to any point xi prime. Because this point is in a line Li, so if I take Li transpose xi prime, should give me 0 because the point is on the line. Now, if I replace this part by the projective of the point, will be actually L transpose H minus 1, like with the inverse of H multiplied by H multiplied by xi. And will give us that the image of Li prime, which is the image, the transformation of the map of H, will be represented as L prime will be equal H minus 1, the inverse of the matrix H multiplied by L. So in order to map a line, all what we need to compute the inverse of the matrix H and multiply this by the line, which is again represented as a vector. The same thing if we take the conics, any conic which will be mapped, if we compute this, we learn from the previous lectures that a point in the conic will be x transpose multiplied by the conic matrix representation, again multiplied by x, will give us a 0. Then we take x prime, which will be represent this as the mapping of the point, which will be x prime h minus 1, because we take the opposite. Then we take h prime minus 1 x from the other side, and will give us that this part, I cannot write in this is okay. So this is what will give us. So in this case, if we take this part as will be the mapping of the point. So if we take the point, the mapping of any point in the conic will be the image, or the image of the point in the conic multiplied by this and the image of the conic. And we know that conic will be mapped in a projective transformation to a conic. Now, since that means the point x prime will be also this equals 0, which is we mean that the point x prime will be in this conic, which is mean that the transformation of that conic C will be represented as H minus T, means the inverse and the transpose, multiplied by C multiplied by minus 1. And this is the map of, this is how we map a conic. A conic C will be mapped to a conic C prime by the same projective transformation. The only difference will be H minus 1 multiplied by, from the other side, by the H minus T, which is in one side you will have the inverse, and then the other side will have the inverse transpose. Is that clear? So this is how we map a conic. We know that a line will be mapped to a line, a conic will be mapped to a conic, will be different conic. So this is, I will give example. We know that a circle, which is a conic, will be mapped, could be mapped to a circle, and could be mapped to an ellipse, which is again still a conic. Could be mapped also to a parabola or hyperparabola. It depends on the viewpoint. Now, this is why here with the same projection transformation will give us also the image of a conic. If you give me a conic represented as a matrix C, then I will be able to generate the representation of the conic image by simple equation. The same thing apply to the dual conic. A dual conic, which is, we said like the last time, which is the representation of the conic in the dual, like, or the dual representation of a conic. Now again, it's the same thing, just here we don't have the inverse. So we know that a point will be mapped to a point, a line will be mapped to a line, a conic will be mapped to a conic. Let's give some examples what we will have. So here we have like various images of the same plane. The only difference we have here is that here we have maybe only change in the size, scale, and again uniform scale. This is, we have a change. All these are like, this is rotation, but this is still square. And here we have, it's not really, because these circles and these circles, which is originally the same size, they are not the same. Here, not that they are the same size, but the circles here become an ellipse. So all these are projective transformation. But it's, now let us kind of like think about the group in mathematical sense of these, all these projective transformation. Just kind of like bring you back to the first year in your undergraduate. Like a group, which is algebraic structure, consists of like set like of elements, which is together like could be a or formed within an operation that combines any two of its elements to create a new element within the group, within this set. This is how we define a group, which is mean that if I have a transformation, or I have an element and I have another element, if I combine them, then I will get a new element which is within the same group. This combination should also like comply with some requirement, which is not really like the scope of this course. And I assume if any one of you would need that, know how to go and how to Google this and get it and kind of read about this. Now, within this like groups, if we think about the projective linear transformation, this is the largest group. Within this group, we have subgroups, which is we have, within this we have the affine group, which is affine transformation. And this is, within the affine transformation, we have the Euclidean group. And within the Euclidean, we have the oriented, like a Euclidean group. Every one of them belong to the projective linear group, but there is a hierarchy within these, which is, what's the hierarchy mean? That oriented Euclidean group, which is, if we represent it, will be a kind of projective linear. If we take an element, if we take an element here, will be a matrix, which is oriented Euclidean matrix. It's a projective linear matrix with some constraint, which is mean some elements are fixed or have to be within some specific range or specific values. So the same thing with the Euclidean. If I take an Euclidean matrix or Euclidean transformation, it is a projective transformation with some elements fixed or have specific values or specific range of values. Now, why we want to look into this hierarchy? Because this hierarchy also imposes on the geometry of this mapping, or the changes within the geometry of the source and the map, or the source and the image. Okay, let us look into each one of these in detail. The first class, which is the simplest one, now we start from the most concentrated one and go out. So this will be the isometrics. The isometries, which is very, as its name, iso, it means the same, metric, which is mean measure, which is the same measure. Isometric transformation, or isometry transformation, this is transformation is the planar, like the two domain, preserve Euclidean distances and Euclidean distances and angle of the object. So since Euclidean distance, it also has to preserve the angles. It's represented as this matrix 3 by 3. Now, this is, as we saw, this is also comply with the requirement of projective matrix. So this is practically projective matrix. But here we have more limitation. We require that the last row should be 0, 0, 1. This is fixed value. This is not a general projective transformation. We require that Tx and Ty could be any values. And we require that only this could be either -1 or +1. Let us look at +1 just for simplicity. If we look at this +1, what we have here, we have very simple transformation. We have a rotation and translation. So what does mean any object or any shape we will take, we can only rotate and translate, which will be the same shape. We don't change its kind of like size, no angles, everything is fixed. We only can rotate and change. Now this is the isometric transformation. It's the only thing its object can rotate and change position. Now, what we will have, the only difference between -1 will be preserving the orientation, and +1 and epsilon taken as a -1 will take actually the reverse orientation. This is the only difference. That object could flip. But again, will be the same size and exactly the same angles. Now, what we will have, if we look at the property of this, will now also will look into a block matrix shape. So if we look at the block form, we could represent this as R, T, 1, and O, or 0 transpose, whatever we take it, where actually T will be any vectors, Tx, Ty. This is 0, which is be 0, 0, and this is 1. And R, the only requirement that this is R multiplied by itself is give us the matrix of the identity. And this is the requirement of the rotation, because cosine square plus sine square give us 1. Okay, this is guarantee that this is the form of this matrix. If they comply with this form and this requirement, this is an isometric matrix. But if we look at what things, if I take a shape and apply to its isometric transformation, this is what we all call rigid transformation. It's used a lot in kind of like mechanics, where you have object could move and rotate, but they don't deform, they don't change shape. This is what we call the isometric transformation. It's invariance. Invariance, what's preserved, which is mean the same property which was in the source will be preserved, will remain on the image. What we have the length, because if we take any object and rotate it, which for example here, this is what I will take. So the only thing I can move and rotate, this is the only thing, which is the length will be preserved, and the angle will be preserved, and the area will be preserved. This is a very, very limited transformation. The only thing which is you can do with the object, can rotate it and can translate it. Now, this will be the most concentrated class. Let us go a little bit out of this, which will be, now we will allow more degrees of freedom, which is we call similarity. Similarity is like what we, practically it's isotropic transformation, which mean scaling, and again translation and rotation. So the only thing now we allow the object with similarity is not only to be what we allowed in isometric, plus ability to scale the object. But again, uniform scaling. We don't allow the object to scale in a non-uniform manner, which mean I have the same thing. The only difference here we have S. So I can scale the object, scale it up or down, and I can rotate it and translate it. This is the only thing which is I have. So how many degrees of freedom I have? Before we have angle and the translate. How many degrees we have in isometric? We have 3, which is the angle and Tx and Ty. So what we have, the angle, which is phi theta, Tx and Ty. This is the only 3 degrees of freedom we have for the isometric. For similarity, we have the same 3 because we have the angle and we have Tx, Ty, and we have more the scale. So we have 4 degrees of freedom. We have the scale S, but the scale along the X and the Y are the same. So it's uniform scaling. And we have the same what we have in the isometric. So we have 4 degrees of freedom, 1 for scale, 1 for rotation, and 2 for translation. So what here, if we write it, we can the same thing. We write it exactly the same, but we add the value S before the matrix R. Is that clear? So what's the invariant? What things preserved in this transformation? Are length preserved? No, because you have scale. So the length are not preserved. Are angles preserved? Yes, so angles are preserved. What else preserved if the length? If I have, let us think, I have take this one. The ratio between the width, the height, and the width of this rectangle is preserved? Yes, so the ratio between length are preserved. This is the ratio of length are preserved. And is the area preserved? No. But if we take the ratio, if we have 2 areas, which is if I have this one and this one, this will be in my domain, and now the ratio between this area and this area, and after the transformation, I will get a new area for this, new area for this. Is the ratio between them preserved? The 2 objects, yes, because the length, the ratio of lengths is preserved. Since the ratio of length is preserved, then area is a function of length. And this is how it's in. Actually, we preserve the ratios of area. One thing which is parallel lines remain parallel? In the isometry, we know that parallel lines remain parallel because angles are preserved. And here is parallel lines remain parallel? Yes, because the angles are preserved. So this is the similarity. Is that clear? So we need to add more degrees of freedom. And if we add more degrees of freedom, we reach the affine transformation, which is quite common that we probably you hear about this because it is the general non-singular geometric transformation. Practically in computer graphics, when when you learn about geometric transformation, we are talking about affine transformation. So the only thing which is we have, it's the requirement of, it's a general non-singular matrix. Non-singular means the determinant is of this matrix is not 0. And it's followed by translation. We take the translation out, just kind of because we take about like just thinking about all the transformation, which is could be rotate and scale, but the scale is not uniform in this case. And then we have translation. So if we think about the affine transformation, we have rotate by an angle, again in the plane, so we rotate around the origin. And then we have scale, which is could be non-symmetric scale. This is why this is compared, so this is non-isotropic. Isotropic means the two direction is the same, just non-isotropic, not necessary. And then we have translate. So what we will have, this is why we will have the general A1. This is the general matrix A1, 1, A1, 2, A2, 1, A2, 2. This is give us the general, this is will give us the scale and the rotate. Then we have the translate Tx, T1. And this is, again, you note that this is 0, 0, and this is 1. So if we write it as a block matrix, the only thing which is we rotate, this is the T as it was before. This is 0. And the requirement that is will be A should be a combination of rotation and scale. And then we have the translate. Now, this kind of transformation, this is what we call the original or the geometric transformation. What's the invariant? First of all, let us see how many degrees of freedom we have. Six of degrees. Let us try to think about it. We have the angle, which is 1. We could scale along the x-axis and the y-axis. We have 2, so that means 3. Yes? And then we have Tx translation. This is how this will give us. Five. Where is the 6? Okay, one thing which is we have, here we have not one angle for it, like the rotation, because we don't require that the translation along like will be with one angle. Not that we have two angles here. One is the rotation before, and then we have this matrix T. This is another angle, which is the rotation after that. This is will enable us to get kind of this kind of deformation. So we have not one angle, rotation we have 2, and exactly it's 6 because we have 2 for rotation, 2 for scale, and 2 for translate. Because one angle will not give us ability to do this kind of like a deformation. Now, what's the invariant of this group of transformation? What things preserved in the source and the image of the mapping? So definitely one thing which is, as we see here, angles are not preserved. This is one thing. So angles are not preserved. Parallel lines, yes, they are preserved. Parallel lines. What else? Scale? Scale, definitely not. But what you say? The ratio of parallel length. Parallel length, the ratio between these parallel lengths are preserved. Not the general ratio, but the ratio in parallel length. And the ratio of area is also preserved. Because this is like, unlike the general projective transformation or perspective transformation, the area of this object, which will be, if these two objects, or let us kind of make it simple. If we have this exactly will be here, and another like one will be here and here, and now I take a photo from here. This area will be the same. In my photo, the area of this posted, this and this will be the same. No, which is mean that the same thing, which is if I have this one inside the picture. In projective or general projective transformation, it's not preserved, because if I have the ratio between this area and this area, let us call it R, this area and this area will be call it R, and between this area and this area will be R. If I have a photo, like a photo of this, in my photo, let us take at this photo, I will have the 4 cards. This will be the small card, and another 4 cards, and another 3. The ratio between this and this will be like R prime. And the ratio between this and this will not be the same. This is why the ratio between areas in general projective transformation is not preserved. But for affine transformation, it is preserved, which is mean because the entire scene goes through the same transformation. So if I have take the same, this kind of scene, which will be cards, like these 4 cards, and apply affine transformation, the only thing which is I'm going to do, I'm going to change the angle of these shapes. I'm going kind of, I'm going to deform this. But it doesn't matter where they are geographically located on the plane, they will go through the same transformation, which is mean this will go through the same transformation and the same transformation. The same with this one. So if the ratio between this area and this area will be R, the ratio will be this one and this one will be R, and the same thing. So this is mean that the ratio of the images of these cards will be preserved. Of the ratio between the area of the images of these shapes is preserved. Is that clear? Okay, now we are going up to the higher level, which is, in this case, will give us the projective transformation. So we started from the most concentrated one, going a little bit out, a little bit. Now this is the least concentrated one. The only thing which is here we require the general requirement of projective transformation, which is what we explained, or what we kind of the preserve of collinearity. That means points which is along the same lines will be along a new line, not definitely same, but will be along new line. That means there is no deformation, non-linear. All the deformation is linear deformation, are linear deformation. So we can write it this way. And in this case, the only thing requirement, not that this is not 0 now. This is the big kind of difference. This is A general matrix, and this is T general matrix. And now if we think about this transformation, the only parallel, let us, we know that here we have 8 degrees of freedom. So we have 2 degrees of freedom for scale, 2 degrees of freedom for rotation, 2 degrees of freedom for translation, and 2 degrees of freedom for line at the infinity. This is the kind of creature which is we have not seen in the area transformation. We did not take, or we did not consider point in the infinity. Here It's actually, we account for that. This is what gives us the 8 degrees of freedom. What things, what the invariant, what preserved from the source and its image, or what preserved between the mapping between the source plane and its image. Let us see. Angles. Let us start with the most simple things. Length. No. Area. Okay. Ratio of length. No. Ratio of area. No. Parallel lines. Ratio of parallel lines. Ratio of parallel lines. No. Which is what's it mean, ratio of parallel lines? That if I have the area of this is, let us see, which is, you can think always in like perspective transformation. If I have the ratio between this one and this one, or if I have the ratio between this one and this one, this will be simple. And they are parallel. So if I have, it depends, this ratio is 1 in the source. If I take a photo from here, this will be small and this will be large. So this will be kind of like a definitely not the ratio between them is not preserved. So this is one thing which is not. The only thing which is preserved in projective transformation is what we will call cross ratio of 4 points. Cross ratio of 4 points, which is, I'll explain it like more in detail later, but this is the ratio between points along the same line, which is a cross ratio could be also kind of defined, not like really 4 points along the same line, but if they are collinear, we can actually kind of like have a simple kind of like understanding of this. Now, before I go to cross ratio and define it, let us look at like the things which is we talked about, which is in the projective domain. We talked about point in the infinity. What was point in the infinity? But it's, which is, we give it kind of very precise definition, which is the point, which is the third component is 0. This is the point, the infinity. And now, one thing which is, let us look at this point and line at the infinity. The same thing, line the infinity is also a vector, which is third component is 0. This is the line in the infinity. Now, or at the infinity. Now, let us apply two kinds of transformation, affine transformation and projective transformation to points and lines in the infinity, or ideal points and line in the infinity. So if we apply this for the affine transformation, we will get this one, which is mean the ideal point, which was in the infinity, remain in the infinity. The same with lines. So this is like the lines remain, the points along the line in the infinity remain along the same line, but in the infinity. They move along the infinity line. And points anyway remain in the infinity. If we take the projective transformation, and this is one thing which is, we could get point which is R in the, not in the infinity, we'll go to the infinity in the opposite, on the perspective or projective transformation, which is mean, if we take the point in the infinity or a line in the infinity in this case, multiplied by the projective transformation, we get component here which is may not be 0. What does this mean? It means that points may get mapped to affinite points. Point in the infinity could be mapped to affinite point, which is very simple. It's very like case, if we take a photo of two parallel lines, like kind of like a, we will see that there is a point in the infinity that they are exist there, which is if we take this or recorrect or like remove the perspective distortion, this point will come from the infinity to some point which is the opposite. Sorry, this point which was supposed in the infinity will appear in the image, and the vice versa. Is that clear? So if we take, for example, let us take the general orthogonal projection, this point of the intersection of these two lines will be in the infinity. But if we take a perspective image of this, these will intersect in some way which is not in the infinity, which is, we call it the vanishing point. The same thing we have with points. So this is the two major properties of affine transformation and projective transformation. Projective transformation can cope with points and line in the infinity and kind of map them, not necessarily to the infinity, but will map them to a kind of like a finite, like points in the finite space. While a affine transformation cannot cope with this. Points which is the infinity will remain in the infinity, lines of the infinity will remain in the infinity. Now, just before I go to the next topic, I would like to just kind of explain I know that you all learned this, and this is, I'm not really adding you, but just refreshing your memory, which is what we call matrix decomposition. Matrix decomposition is a process which is take a matrix and fractalize it into multiplication of several matrices. Usually we do that to simplify the computation or simplify the solution of a linear system or compute various properties. It's application driven how to decompose this matrix or any given matrix. Some decomposition work for square matrix, some decomposition work for non-square matrix. So let us take the general, the very simple case where if we have a matrix A, we will decompose it into two matrices, L, which is the lower triangles, and U, the upper triangles. That's quite very common way. If you decompose the matrix into two matrices, you can solve a linear system. And this case requires that A to be square matrix, a linear system, very easy. We can also do subdivided a matrix into LDU, which is also common decomposition. We have the lower, again, we have the upper triangle and the lower triangles and the diagonal matrix. This is another decomposition. We also, one of the most common used technique, which is called the singular value decomposition, which is take a matrix and decompose it into three matrices, which is comply with this U, D, and V, where D is a non-negative diagonal matrix, and U and V are unity matrices. The same thing, this is quite common to compute, usually used to compute the eigenvalues, or often in order to take the matrix, reduce the dimension, space dimension. We also have the eigen decomposition, which is pretty much based on the eigenvalues and the eigenvector into three matrices, V, D, and in this case what we will get, the D is the diagonals and the eigenvalues and the eigenvectors. The same thing, we could actually look at the projective transformation or projectivities. We can decompose them into three matrices. But we don't, here we want the composition to comply with some requirement. So for example, here we want to subdivide this into three matrices, which will be AS, AP, HS, HA, and HP, which is, if we multiply this together, will give us the projective transformation. Now, one thing which is, if we think about this, the subdivision will be taking as in order to create a affine transformation. So let us look at this one, for example, what we will take. What this matrix like remind you? Similarity. So the only thing we have rotation and scale and translate. The second one, which is will give us a K. We don't have translate here because the translate is taking into the first one. But this is to remind us about the affine transformation, yes? Because this is the K is in general. This is the unity matrix. And this is comply for the part of the projective. Because this one is 0 and this one is 0. Now, which is mean, now if why we need to decompose this into 3 transformation, which is 2 of them. One is similarity, which is more like kind of more like I would say less constraint. We started with similarity, then we have the general affine transformation, then we have the projective. Yes? Now, like if we think about this, very simple example, if I have this transformation in general, if I decompose it into these 3 transformation, what I understand that I have, this is similarity, and this is the general affine transformation, and this is we will have the projective. That's clear? Definitely there are algorithms which can create this decomposition. Now, why one would need to do this work? Why we need to do this work in order to decompose projective transformation? Theoretically, it's interesting problem. Mathematicians also like kind of to create. This is also one thing. But why we may need this? What's the motivation behind the decomposition?
Maintain accuracy of the visual part. So when it's moving or whatever, it appears real.
Yeah, maybe it kind of like to could be, but this is not the main motivation. Sometimes we don't want to do the entire projective mapping. For example, if I want only to measure the length or the ratio between length of these transformations, I don't need kind of the entire like a transformation, projective transformation. It's enough maybe for me to recover some part in order to do the computation. For example, if I only reduce if I want, for example, I would say if I want to measure the length ratio in my image, I don't need kind of like the entire projective transformation. It's enough for me kind of to recover up to similarity. So this is why I don't need to do the entire computation. If I recover up to similarity, I can compute the length ratios. That means if you have a specific requirement which doesn't require the entire projective transformation, you could do part of the transformation. This is the main motivation for this. For example, if I have this matrix and I can maybe do this part, which is in order to do the perspective distortion. If I apply only this part, the remaining object will take, let us call this matrix just too simple, S, A, and P, okay? So if I have point x, I multiplied by this matrix, I can do the same. I can do SA, this is one part, and this multiplied by px. Now, the product of this is do the rectification. It's correct the perspective distortion. That means after this, my image will be without perspective distortion. And this will be maybe kind of things which is I want to do in this. If I want to compute, for example, the length ratio, that's enough. Then if I want to add another one, which is if I want now to take for any point, which I will here, we recover the rectification, and I also recover the affine transformation. And now the only thing which is remain for me is the similarity. So this is why the decomposition is kind of useful when you want to like part of the information within the image and not the entire information. Like some kind of specific properties you would like to recover. So you go up where is this property is invariant. And that's enough for you. You don't need to do the entire computation or the entire determination of that matrix. That's clear? Okay. Now just let us kind of to refresh your memory about the transformation hierarchy. We have the least constraint one, which is the projective transformation, which is this is how it's represented in general. The only thing which is preserved is the collinearity, which is collinearity is not really by itself. It's not hard to kind of like take advantage of this. But the big actually thing which is preserved is the cross ratio, which is I will explain next. Other than this, pretty much nothing is preserved. It's the collinearity and order of contact actually came as a result of the cross ratio. Then we go to the least, a little 1 degree below or 1 level below is the affine transformation, which has 6 degrees of freedom, which is what it allows. If this is the source, it actually could allow rotation by, again, 2 angles, because we want kind of like ability to also deform the object, translate, and what's the other 2? Scale. So we have 6 degrees of freedom. What we preserve here, the ratio of areas, parallelism is preserved definitely, the ratios of areas, ratios of length, and parallel lines. Then the 1 degree below, which is similarity. Similarity, what we have, object could pretty much its rotation and the translation. Rotation and translation and scale, but uniform scale. And this is what we preserve here, ratio of lengths and angles, and Euclidean oriented, which is the most concentrated transformation, which is 3 degrees of freedom, to preserve length and areas and angles. We should add angles here. And that's everyone, the matrix encode this kind of limitation. Is that clear? Okay. So let us go into the cross ratio. Cross ratio is also called double ratio. This is from like and it's a special association of 4 points or 4 numbers in general. And this is the ratio between them. If we have Z1, Z2, Z3, Z4, what we call the crest ratio will be Z1 minus Z3 multiplied by Z2 minus Z4, which is the ratio between the 2. And then the other ratio, Z2 minus Z3 multiplied by Z1 minus Z4. So we have the 4 combination of these like 4 numbers, which is, this is what we call, it's usually why it called the double ratio. If we write it as Z1 minus Z3, Z2 minus Z1 divided by Z1 minus Z4 and Z2 minus Z4, which is mean this is a ratio and this is a ratio and this is a ratio of a ratio. This is why it's called double ratio. This is why it's kind of like one of the interesting things. It was talking even during like Euclid times. He was one of the people who even like thought about this as kind of like a very ratio of ratios, which is interesting. Now, if we have the 4 points, not general 4 points, collinear, which is mean they are along a line, which is the interesting part for us. So if we have the 4 points along the lines, this cross ratio is preserved. That means the cross ratio here and the cross ratio here are the same. And in this case, the cross ratio of the 4 points AB and CD will be AC multiplied by BD divided by BC multiplied by AD. This number will be here and the same will be here. And this is the only ratio is preserved, of course, collinearity and the projective transformation. Is that clear? Any question? Okay, so I'll summarize what we have done in this lecture. We have started with the definition. We actually go over again the definition of the projective transformation. Then we looked into the hierarchy of transformation within the projective group. So we looked into 3 levels of hierarchy. We started with the most concentrated one, which is what was the most concentrated one? The isometric. The isometric is the transformation which is only include rotation and the translate, which is mean it preserve the length, area, angles, and parallels, which is pretty much the most concentrated transformation. Then we go the next one in the level, which was the similarity, which is in addition to translate, a rotation and translation, we have also scale, but uniform scale. And that will give us the ability to preserve the angles, parallel lines, and ratio of lengths and ratio of areas. And then when we go up to the upper, like the another level, which is the affine transformation, which is this transformation, for us it was 6 degrees of freedom because we have 2 for rotation, 2 for scale, and 2 for translate. It preserve angles. Preserve angles? No, it doesn't preserve angles. Does it preserve area? No. Does it preserve length? No. It preserve the ratio of parallel lines and preserve the ratio of area. And then we move to the general projective transformation, and then that's the most general group, which is include the entire all these groups, which is the only thing which is it's preserve collinearity as we saw, and it's preserve the cross ratio. So these 2 things, we see how we can decompose these into matrices, like the 1 projective matrices into 3 matrices, and like we know how like to recover the like or how to rectify or remove the perspective distortion. Next lecture, I'll talk about how to do more practical and kind of like recovering the distortion of perspective projection using the vanishing point. We'll define what's a vanishing point, and then we look into kind of more practical algorithmic kind of approach to kind of apply these kind of technique to images in the 2D domain. Okay, so I'll stop here because I want kind of like have to start something and go, and we will continue the next week. Next week we'll have a lecture unless someone have really objection or some like limitation. Then 2 weeks after I will not have a lecture, I think, or 3 weeks, I'm not sure. So we will kind of see which is Friday will be okay for us. Okay, and thank you, and see you next week.
Thanks.
Any questions?